the 4 different categories of the flip-flops, right? So we already have the SR, we have the JK, and we have the D flip-flop, and we have the T flip-flop. That makes sense? What we learn out of it, we learn the story coming from the latch, right? And in the top of that, we came into the conclusion to fix the problem with the SR by building the JK flip-flop. And traditionally, JK flip-flop introduced a new problem, which is the oscillation, that was fixed by adding extra cascaded latch reporting on the opposite of the edge of the clock. And that actually made it toggling. So, the state exists, but it's toggling. So now, we, fixing the oscillation and introducing toggling. Then just a matter of organizing the whole entire work, taking the 2 states of reporting the data without any relation with the current state that's producing data, flip-flop. So it's a flip-flop associated with data. And when we say associated with data, that means, we are actually moving data from the input to the output based on the positive edge of the clock or the negative edge of the clock, depends on the edge. Then out of the also JK flip-flop with wiring both of the J and K with the same wire and hooking into T, we built something that's called transition flip-flop. And when we say transition flip-flop, it's basically flipping the state or storing the state. That means taking 0, 0, and 1, 1 of the JK in the consideration, right? Later on, not now, but later on, we'll figure out D flip-flop is the best for data / register / memory implementation. While in the transition, that will be really good fit for building counters. And this counter can be up or down or, round counter or irregular counters. All of these things, we're going to talk about it later. But, at least we know the story of every single element we have in the sequential circuit, right? In terms of implementation and learning, how can you move into the design and understanding what is this? We learned something is called truth table, which is initiated by the learning of the SR and putting the clock in the consideration. We learn also the clock and how the clock works, and what type of requirements and specification the clock it has to be following, so we can call this signal or stream of pulses clock. Then we learn there's something is called characteristic or state table, which is combining the present and inputs and forecasting what will be the next state. And after that, we learn from the current and the present, the current state and the next state, we can come into what will be the next input when we are looping back, especially in the sequential circuit. The whole idea is introducing delay. So that's called excitation table. So far, is there any question? Huh? Hello? Excuse me, hello?
Yes, Professor.
Everything's clear?
Yes, on my side.
For every single member of this class, everything is clear? If it's clear, we're gonna move into some tricks to see whether that we know what we are doing or not, which is basically one of the possible things that is to start using the elements of building sequential circuit, or also converting from one to the other, which is called flip-flop flip-flop conversion. So you have a certain flip-flop and you would like to get another flip-flop, right? Let's see how can we do this. It's very straightforward. We have to follow some steps, which is basically identifying the available flip-flop and what is the required flip-flop. What does it mean? It means that I have D flip-flop. I would like to have JK flip-flop. So who is actually the available? D flip-flop. Who is actually required? JK flip-flop. That makes sense? Then we will make the state or the characteristic table for the required flip-flop, so we can start moving toward the implementation. So we can have the make the state or characteristic for required flip-flop. That would be followed by making the excitation table of the available flip-flop. Making excitation table of available flip-flop, and we will ending up with what? Our lovely part, which is basically optimization, if it's possible, using what? K-map. As you know, this is our official way and fastest way to do optimization instead of using the chapter 2 postulates processes. And then, you know, we're gonna go ahead and we will do what? We will write the Boolean expression representing the relation between input and output, and that will be followed by drawing or implementing the circuit. So those are scientific steps. So if you have a problem telling you that I have a flip-flop, I would like to move to another flip-flop, you have to follow those. Like, you know, I need to know what is my available, what is my required. I need to put the characteristic table of the required. Then I will start using the excitation table on the characteristic one. Then I will be able to define what is the inputs for the new one. Then I will just use the Boolean algebra with the optimizations for K-map or whatever. Then we'll do implementation and we'll be done the process. Theoretically, everything looks normal to you before we start using the steps on real problems?
Yeah, it looks pretty clear. Thank you.
You're welcome. So now let's start applying the theoretical steps into the practical problem. So what is the practical problem? I have a JK flip-flop. I want to convert it to be D flip-flop. So JK to D flip-flop conversion. JK D flip-flop conversion. JK to D flip-flop. So who is D flip-flop here is the required. Do you agree? So now, you know, we're gonna move into the steps. So, you know, step number one, you know, our required is the D flip-flop. Our available is the JK flip-flop. Do you guys agree?
Yes.
The second step, we know we're gonna put the characteristic of the required, right? Who is required? D. So the characteristic, it's basically the input will be the current state with the input, and the output will be the next state. So, you know, for D, it's very straightforward. So I have a Qn, and I have here Qn plus 1, and I have D, and I have 4 states, right? 4. 0, 1, 0, 1, 0, 0, 1, 1. And we know that, you know, D flip-flop is just like what transferring from the input to the output, right? So they're gonna be here 0, 1, 0, 1, like that. Make sense? So this is the characteristic of required flip-flop. So far so good?
Yes.
Okay, now we need to get from this table, using the excitation table, what will be the input for the available flip-flops. Did you hear what I said? So this is the characteristic, right? So I'm gonna extend this like this and say, you know, I have here Qn, and I have D, and I have here Qn plus 1, and I have here 0, 1, 0, 1, 0, 0, 1, 1. And I know that it's gonna be 0, 1, 0, 1 because it's exactly as the T. And that was our characteristic. Now I'm extending the table to be excitation table of the available flip-flop. So available flip-flop is JK, since it's excitation. And what exactly I'm gonna use in this table, I'm gonna use this and this to produce the J and K. So now I'm using excitation to bring those. That makes sense?
Yes.
Okay. In that particular case, I don't remember literally what is actually the excitation table of the JK flip-flop. If you guys remember, you know, either that you remember or, you know, you can just do the process by yourself. And, you know, we already have that process before. So if I remember correctly, it was Qn plus 1 and J and K 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. I don't remember very well, but I remember it was 0, 1, like X, X, and then X, X, and 1, 0, something like that. If I'm correct, and I think I'm correct. You guys can revisit. If you don't remember, there is no problem, right? What you can do, you can just do exactly that as I did before, right? You make the SR and then the JK, and then, you know, you start filling the truth table, and from there you can get this.
Mine's backwards, but I think it's just variables, so it should be okay.
I think it should be okay. I think no, I think this should be the right one.
Okay.
You double check, but I know that should be the right one. Okay. Anyway, so now I'm start filling the 4 states, right? So let's fill the 4 states together, right? Now I have Qn0 and Qn plus 1, 0. So I'm talking about what? Qn0, 0. So I'm talking about U0x. Right? Then I have here 0, 1. So I have here 1x. Then I have 1, 0. So I'm talking about what's x1. And here is 1, 1. Oh, sorry. 1, 1. They're going to be what? X0. So in that case, I already filled what I'm looking for the JK flip-flop. Right? Now, what exactly I'm going to do, I'm gonna make the truth table, the implementations using what? Implementation of the equations, which is basically gonna be based on the Qn and the D and Qn and D. So, you know, even though I use these 2 guys to produce J and K, but in reality, I have these 2 only inputs. Do you guys agree?
Yes.
So in that case, you know, I have 2 K maps. One is basically like this. It's going to be Qn and D. And I have another one, which is also like this. And they're going to be Qn D. Then I will go there and see, you know, J, it was 0, 1, 0, 0, 1, X, X. I'm right? 0, 1, and X, X. Another one, it was X, X, 1, 0, right? So that's for J, and this is for K. So pretty much I can write J as a function of Qn and D is equivalent. K as a function of the Qn and D is equivalent. Then I will check here. This X, I can use it. Do you guys agree? And I can say J is equal D, right? J is equal D. Then for this particular one, I'm saying that, you know, K is going to be D what?
Complement.
Complement. So here going to be what? D complement. Right? Any questions so far?
No.
So now implementation, right? I have here my JK. Here is JK. And I have here my clock. And I have here the QN. And I have here the QN complement, all right? Then I will go ahead and say J was D. So I have D here. And basically I can just connect it like that. Then, you know, I have K is the D complement. So basically, you know, I can take the complement like this and they're gonna be, and that's basically my circuit. And it looks easy lemon squeezy. And this is basically the implementation of D using the JK. Any question? Any questions? Any answer? Any concern? What is the best way to do this work in a very efficient way? Practice. Do you guys agree?
Yes.
So let's practice with another problem. You know, we have a lot of time, right? So practice with another problem. What is the problem? SR flip-flop to JK flip-flop. We know SR and JK, if you guys remember, the difference, it was that loop back thing, right? You remember that? Anyway, what is my available flip-flop? SR. What is my required flip-flop? Somebody can tell me.
JK.
JK, yes. Then we say we put the characteristic table for what? For the required, right? Characteristic table for the required. So that means, you know, QN, JK, and QN plus 1. Then I know that, you know, I need what? SR here, right? Then I will go like this: 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. And then, you know, when you start filling this based on the information we know about JK, I don't have it in my hand, but, you know, maybe I can search in my old documents. Or we can actually get it here in the side, right? You guys remember how can we didn't make it, right? It was like this, right? It was NAND 1, 2, 3 like this, right? NAND, and that was the clock, right? Then we have here the J, we have here K, right? And then we have here like this, we have here like that, and then we go like this. And if I remember correct, it was like this, and then, you know, we're gonna go here like this, right? Do you remember this? That was the definite, that was the design before we fixed the problem of oscillation, right?
Yep.
Yes, which still can be used, but, you know, of course, you know, the other one is the high end. Anyway, and we know our NAND, if you remember, also X, Y, and Z, 1, 2, 3, 4, right? 0, 1, 0, 1, 0, 0, 1, 1. And then, you know, here we're gonna be 1, what? 1, 1, 1, 0, because this is NAND. Everybody's following me? Now we're gonna start see those values, how we're gonna fill it, right? So if I remember correct, from the latch, right? If J equal 0, 0, do you remember that? Do you remember the latch? It was what?
1.
So, you know, if anything was 0, the output will be 1, right? So they're gonna be 1 like this, right? If anything is 1, So those guys will be flipping each other, right? So that means it's gonna be what? Gonna stick as it is. So gonna be storing. So storing, that means 0 will be 0, right? Same thing here. 1 is gonna be 1. You guys remember that?
Yes.
Now, 1, 1. That was 0, they're gonna be what? 1. That was 1, they're gonna be what? 0. Right? Then the one in the middle will be deciding for us, right? The one in the middle is gonna be here 0, 1, they're gonna be here 0, 1. Doesn't make any sense. So see, did you see how I filled it? Hello? Hello? Hello?
Last time we did it, it was 0, 1, 0. Does it not matter? Is it arbitrary?
No, 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 it's not arbitrary. Basically, maybe last time because I make it a NOR in my head. So
Okay.
in an AND completely, look, 0 here, 1, 0, 1.
Okay.
In general, I'm just telling you concept, but you have to follow with by your hand and you fill by your hand, you know what I mean?
Okay.
That makes sense? So Gabriel, does it make sense to you?
Yes, sir.
Okay, what about the rest of you guys? If it makes sense, please, just give me interact. Tell me it makes sense or not. If it's not, we can work on it. It's not a problem for me. Okay, in that case, we just need the excitation table of the SR. So the excitation was X, Q, and QN plus 1. And here's an SNR 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. And also for you guys, don't remember when I told you last time when I was making the flip-flop, something was flipped. And I told you just double check by yourself when you are filling the thing. So that's why, you need to check all the numbers again. If you guys revisited the recorded lecture last time. Okay, so if I also remember correct, the excitation table for SR, it was 0x, and I think that was 1, that was 0, I think that was X, and I think he was 1, and I remember that was 0 and 0. Okay, so we're gonna take this, and we can look to our table and start filling the S and R, right? So, when I see 0 here, and 0 in the QN plus 1, that's indication SR will be equal 0x. When I see 0 here and 0 there, 0x. When I see 0, 1, 0, 1, what? 1, 0, and I see it again, 1, 0. Then, it's gonna be 1, 1, right? So 1, 1 is what? X 0. And then 1, 0. 1, 0 is 0, 1. 1, 1 again. 1, 1 again is what? X 0. Then 1, 0 is gonna be 0, 1. So what I did now, I filled the SR, right? So a third or the fourth steps is actually to look into S as a function of the 3 and to look to the R as a function of 3. So we're gonna have 2 K-maps. So in this case, my K-map is gonna be 3 var, 3 variables, and those variables from the left to the right. So I will avoid the orthogonal K-map. So gonna be QN, JK, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 3, 2, 4, 5, 7, 6, right? So gonna be what? M2 is 1. M2 is 1. M3 is 1. M3 is 1, right? M4 is X. M4 is X. M6 is X. And that's it, right? And that's basically what S as a function of the J, oh, sorry, to be more organized, to be as a function of the Q and J and K, right? Somebody tell me what the answer will be. Hello? What the answer will be? How many groups we have? K-map. Hello?
You can do 2 groups or
Sure.
1.
Make sense?
Yes.
They're going to be Qn complement of this. And then, I have this going to be J. They're going to be ORed with this, which is basically going to be JK complement. Right?
Yep.
Then you're going to go make the second K-map. One. Going to be also Qn JK 000111110 0 1 3 2 4 5 7 6 0 1. Then they're gonna be associated for R, right? So gonna be location 0, location 1 is gonna be X. Location 0, location 1 is gonna be X. And then location 5 and 7 will be 1. 5 and 7. Where's 5? So what does it mean? It means just one group, right? So in that case, R will be this one, which is standing for Q and then they're gonna be what? K. Any question?
Nope.
Somebody needs to tell me, is this correct? Huh? Do you think what I did here is correct?
You could just make one group instead.
Exactly, it should be actually one group. I made the mistake and I wanted somebody to correct me. So
So it should be just one group with
that's it.
Yeah.
Because I don't need this X. Right?
Mhm.
Everybody, you know what I'm doing or not? Everybody align with what I'm saying? Because I already group ones here, right? Why I need to group X? Nobody even told me, nobody told me. So anyway, so now we have J with Qn complement, and what? Qn with K for R, right? Which is basically what we did before, right? If you remember very carefully, I have here, my S, and I have here my R, and I have here my Q, and I have here my Qn complement, right? And I have here my clock. Then I just need here AND or NAND or whatever you call, and then you just go here and just go ahead there. And then I need to do like that. This one will go like this. They're gonna be with J, and that will reduce the Qn. And this one will go like this, and they're gonna go with K, and that will reduce R. And that will be our implementation. You guys agree? And that's exactly what we already have done when we fix the problem of SR by introducing the feedback control. And then, we receive the toggling in 1.1. Make sense to everybody?
Yep.
Super. What about if I like to move from SR to T flip-flop? Same thing. Right? What's going on there? Anyway. So in that case, you're gonna do the same thing. I have here my table, I have here Qn, just Qn, I'm sorry. Qn with T, and this is the characteristic. Qn plus 1 is the output. So from here, this is the characteristic of the required. Then, you know, gonna be 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. And then, you know, out of this SR, so basically SR will be here, and that will be associated with the Qn and T. You guys can try by yourself like a practice. Professor, can you scroll up to see the clock? What, the circuit? Where? This one? Alejandro, is this one? Yes. Anyway, you know that, you know, under the supporting folder, I put a copy of the handwriting notes in every single week under the learning units. Alejandro? Yes, just I want to be sure that you know that, right? I put a copy of the recorded video under the recorded lecture folder, and I put under supporting the copy of the handwriting as a PDF. Okay, so filling this is not really hard. Everybody agree with me?
Sorry, Professor, was there a Qn in the circuit? Is there supposed to be Qn? It's just be Q and Q complement, no?
What do you mean? What? This is Qn and this Qn plus 1.
No, in the circuit. If you scroll up, isn't that supposed to be just Q, not Qn?
Yeah, this is just Qn. Because you know who is defining the present and next?
Okay.
Right? Like this. Right?
Mm-hmm.
Make sense?
Thank you.
You are most welcome, sir. Anyway, is the subject is clear or not? Also, you know,
Yes.
you can make it like this: T flip-flop, D flip-flop. Right? You can do whatever you want. So you will find it is really easy, you know? Sounds easy? I have something, you know, I wrote a couple of years ago. I can share it with you guys on the supporting folder as well. So I'm gonna leave it there. You know, I have it's called flip-flop conversion. So you guys can even see it, you know, with all the revisions, with numbers and everything. Okay, Luke?
Sounds good.
Yes, that'll be cool.
Super. Now, there is a fantastic question. What is this fantastic question? Have you guys heard about something called circuit analysis?
Maybe.
So what is circuit analysis? Some people actually teach this, some people not. But you know what I'm trying to say, I can draw for you a circuit and I ask you to give me the whole entire circuit analysis. But before you do this, you need to learn something is called FSM, which is called finite state machine. What's called again? Finite state machine. What does finite state machine means? A finite state machine, it is a way to define the next state from the current input and current state using graphical representation. There are two different types of finite state machine. One is called Mealy, one is called Moore. Mealy, you know, you guys know that my email address is mealy@cvp.edu. Have you guys ever tried to send me emails? You know, it's called maily at CPP. So, you know, every time, you know, you forget it, just remember this. So that's called maily finite state machine. That's called more finite state machine. Each way, it has its own pros and cons. But, you know, what does it mean, graphical representation? The graphical representation of any finite state machine is starting from what? Is starting from definition the state as a bubble. So the tools we use for building finite state machine, you know, bubbles, arch, and conditions. So I give you example for instance, okay? If I'm in state S0, so this is my current state, and I'm going to state S1 with a condition that this input is equal 1, but while that input equal 1, the output equals 0. So what I did, I built here a branch of the finite state machine. And since I put on the arc here, the input and the output, this is actually maily finite state machine. We can have a lot of examples, so don't worry. I just need you to just follow. So, you know, finite state machine, it's a way of defining the next state from the current input and the current state using the graphical representation. How many type of the state machines we have representation? We have maily and we have more. Maily, you know, you have actually, you know, the tools in your hand to build any finite state machine graphical representation, bubbles representing the state, and arcs representing the transition from the state to the others, while there is a condition on the arcs telling me why I'm going from one to the others. Guess who is actually, we learned so far about, which is using the finite state machine? Huh? State table, characteristic table. State table. Do you remember when I told you it's called characteristic table or state table?
Yes.
So see, now we are using it. So let's actually try to build a graphical representation of any of the state table we learned from the flip-flops. So, you know, why we don't look into our previous example of the, for instance, this JK, right? Let's take it in the bottoms and start working on it. That makes sense? So what we can do, we can just like go ahead like this and starting the whole entire thing as a QN and J, K, QN plus 1. So here is the current state with associated inputs deciding who is my next state. This is one of the things telling me that, you know, I can use a finite state machine graphical representation. Everybody know that it's an 8 state table, right?
Yes.
4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, then 2, 3, 4, 1, 2, 3, 4. Right? Then, you know, if you guys remember, that was actually 1, 1, everybody know it, and 0, and that's gonna be 0. So 0 gonna be 0, 0 gonna be 1, you know, 1 is gonna be here 1, 1 is gonna be here 0. And I remember it was 0, 1, and then 0, 1 here. Right? Now, this table is covering how many states? Somebody can guess how many states we have.
8 states. Is it output? So 2 states?
We have 2 states, 0 and 1.
Yeah.
So there is a state called 0, and there is a state called 1. There is a state called 0, and there is a state called 1. Did you see that? So that means, you know, I can donate names for the S when the QN equals 0, I can call it S0. When is actually equal 1, I make it S1. So I have S1 and S0. So how many states this thing is actually doing? 2 states. Why? There is a relation. Number of states, okay, determined by number of flip-flops in the circuit. So this example of this table representing what? JK flip-flop, just one flip-flop, right? Do you agree?
Yeah, just one JK flip-flop.
Exactly. One JK flip-flop, that means it will produce 2 states. Which is opening the door that, you know, if I know that my FSM is representing 8 states, if I know that, you know, my graphical representation is representing 8 states, right? This is an indication that I have to use log 2 of 8 flip-flop to implement such finite state machine. Do you agree?
So you require 3 JK flip-flops or JK or
Whatever
any
flip-flops.
flip-flops?
Whatever flip-flops. Look, this is general stuff, right? It can be any flip-flop. That's actually opening the door about how can you make implementation. But now I'm not talking too much about implementation. I'm talking about, you know, there is something called graphical representation. Later on, we're gonna move into scientific way. Do you remember the theoretical way I followed with you to move from flip-flop to the others? I'm gonna write down to you also steps like that. But at least I want you to think about it. State machines, something represented for the sequential circuit behavior. Okay? A state machine is a graphical representation telling me what is the next state based on the current state and the input. Do you agree? Then how many states, how many flip-flops, this is the relation. So if I say that my finite state machine as a graphical representation had 8 states, that means S0 to S7. So that means, you know, if I want to build a circuit processing this, I need log 2 of 8, which is the 3 flip-flops. Why? Think about it, right? One flip-flop is giving you 2 states, right? So that means log 2 of 2 is equal 1 flip-flop. That makes sense? Hello? Everybody agree? Everybody aware of what I'm saying?
Can you have 9 states?
Oh, good. If you have 9 states, then you have to follow the biggest number closest to 9 states to give you something log 2.
Oh, I got it.
So that means you're gonna use 16, right? So because log 16 is gonna be what? 4.
4.
Then somebody will tell me, what about the rest? The rest are not used. I don't care. Then we're gonna use don't care. Make sense? Now back to the example of at least one JK flip-flop. So at least you can see today there's something called finite state machine, and then later on we can move forward. Okay. So now I have this S0 and S1. So let's start it, right? I have here a bubble, as I said, it's called S0, which is representing Q equals 0. And I have another state is called S1, which is representing Q equal 1. So each one by itself is a current state. But, you know, when I move to the other, it's going to be next for me, right? So now, you know, if it's 0, 0, that means, you know, my current going to the next, right? So my current is 0, going to the next is 0 when JK equal what?
0.
0, 0, right? So let's apply this. My current is 0 going to is 0 when jk equals 0, 0. Here's the arc, right? Okay, perfect. Let's move forward. My current is 0. My next is 0 when the jk is what? 0, 1. So again, my current is 0 going to the next is 0 when the jk is what? Where is it? 0, 1, right? So gonna be here 0, 1. So I can actually remove this 0, 1 and I write what?
0x.
0x, yes. I don't have any outputs, so I don't need to report any output with a slash. If there is anything with output, you can just slash and report here the out. But I don't have, so bye-bye, I don't need output. That makes sense? Now we're gonna move forward. So how many steps we finished in this table? Oh my lord, what the heck? That was one here, right? Now I'm in 0 and I'm going to 1, right? Do you guys agree? So I'm in 0 going to 1. I'm in 0 going to 1 when j is equal 1 and kx. So I'm gonna be here 1x. Then I am in 1 going to it myself when is 0, 0. So I'm in 1 going to myself when is what? 0, 0. Then I'm in 1 going to 0. So that means I'm in 1 going back to 0. I'm in 1 going back to 0 when it's 0, 1. Then I'm in 1 going back to 1 and 1, 0. I'm in 1, 0. So here it can be what? X, 0. Then I'm in 1 going to 0 and 1, 1. I'm in what? I'm in 1 going to 0. I'm in 1 going to 0 when is what? 1, 1. So this can be removed like this to be what? X, 1. So what I built in front of you now, the graphical representation of the Mealy finite state machine representing what? JK flip-flop characteristic state table. Any question? You don't need actually, you don't need to put this like this, this is useless. This is just like, for representing to you, but the thing in front of you now, this is the finite state machine using Mealy representing what? Representing the JK characteristic table. Any question? Hello?
Yeah, I think that makes sense.
It's a piece of cake. So, let's summarize what we learned today, right? Today, we started the whole entire discussion by, reminding ourselves that, the elements used for the sequential circuit are the SR flip-flop moved to the SR latch moving to the SR flip-flops, fixing SR flip-flop, moving to the JK flip-flop, fixing the JK flip-flop, trimming into two different things, which is the transition flip-flop and the data flip-flops. We found out that, we need to have 3 different type of tables describing the whole entire characteristic of the 3 or different 4 flip-flops, which is basically the excitation table or the characteristic state table and the twist table. This table is basically the one we start with. We move to the characteristic. From the characteristic, we move to the excitation. Then we move into moving from one flip-flop to the other using a scientific steps by defining what is the available, what is the required, defining the characteristic table of the required. From there, we can apply the excitation of the available. And after that, we'll do the Boolean algebra or Boolean equations coming from the K-map as optimization techniques we learn. And then, we'll start making implementation by using the flip-flop and, surrounded by some gates to make a connection between of the available and required. We tried many of different examples, and then I left a couple of you guys just like, to think about it. Then we came into conclusion, there's something that's called graphical representation, representing the current and the present state, the current present state and the next state relations based on the what is the input and what is the consequence of the output. We call this finite state machine. We learned there's two different types of finite state machine. One is called merely finite state machine. One is called more finite state machine. The one we use for implementing as an example, it was merely finite state machine. And the specific example we ran, it was the JK characteristic or the state table. We're gonna continue next lectures on the difference between the merely and more with more massive examples. And after that, we will go into the sequential data analysis, which is basically having the circuit and then asking you to return it back to the state diagram, or moving from a state diagram to make implementation as a circuit. And then we'll be done with that, and after that we'll start moving into counters and registers and memory. Any questions?
Nope.
That was really fast.
And recorded.
Yeah. Yeah, sounds good.
Okay, so if there is any problem, you can stop me. Maybe I'm fast, but you can slow me down, right?
Definitely.
By asking to repeat. Then I repeat.
Sounds good.
Sounds good, guys?
Yep.
I hope that you guys are enjoying this course. So far, I'm enjoying talking to you, and I hope that you guys are safe and sound. And I wish you the best of luck. And I wish you the best of the rest of the day. And also, I'll see you next week, and have a nice weekend as well. God bless all of you. A copy of this recorded lectures will be posted by end of the day. A copy of the handwriting notes will be also posted under supporting material for the week 10. And also the instruction that I mentioned to you, I wrote it by my hand long time ago. It will be there as a PDF. Okay?
Thank you, Professor.
Thank you, guys.
Thank you.
God bless all of you. I'll see you on Monday. Thank you.
Yeah. Stay safe, sir.
Bye.
Thank you.
Thank
Bye-bye.
you, Professor.
Thank you. Bye-bye.